Okay, good afternoon. Today is June 28th, and we're going to basically close chapter 3. Okay, chapter 3 has one last subchapter on how to summarize the solution process. And then there is one classical parameter in our area, which is the encounter frequency. So we're going to deduce that. And basically that's it, okay? So that's the first part of the session. And then the second part of the session, I'm going to answer questions, clarify what you need to calculate for this assignment 3, okay? Basically that's the agenda for today. Okay, so let's see. Giovanna, can you see my screen?
Yes.
So this is, I think this is what we saw. Let's go back. Just let's review this full 3-4 subchapter. Okay, this idea, it's basic. It has to be in your mind. Okay, is the fact that when we calculate excitation, we consider two. Some people call it components. I don't know if you can call it components, but anyway, it's like two extreme situations. In one case, we use Frobel law, and that means that we consider that the wavelength is much higher than the dimension of the object under which the waves are acting, okay? And because of this, basically, the wave passes around the object as there were no object at all, right? So for this component, basically, what we do is we obtain the pressure from the solution of the gravitational wave problem. So we apply Bernoulli's, linearized Bernoulli's equation minus rho phi of t, and that's it. So it's like the wave passes and there's nothing there, okay? So we calculate pressure, multiply by area, consider the direction, and then take the vertical component. That's it. The other part is the diffraction. In that case, because of the relationship between the wavelength and the dimension of the object, okay, we can expect a lot of reflected waves, and also behind the object, there could be a very not noticeable area where basically there is no waves. And that's because the dimension of the object is important. So in this case, we call it diffraction component. The interaction between the waves and the whole surface is extremely important, okay? So this is a general expression for the vertical component, okay? So we multiply pressure times ds, that's the amplitude of the force. If we multiply by n, that gives you the vector characteristic of this force. In this case, n is pointing towards the fluid, okay? And since we want to calculate the force on the object, on the hull, we need to include this negative sign. In some cases, people use the n in the other direction. And in that case, you don't need the negative here. But it's a good idea, because in the Bernoulli's equation, there is another negative. So if we can cancel these two negatives, and we get a little bit of simplicity, just a little bit. And then what we do is we take the dot product with the K. K is the normal, unit normal in the upward direction, okay? That's this one here. So the result is just the component in the vertical direction. That's what we're looking for. We integrate that over the whole surface, okay? So for the Froh-Dekry law, so what we need to remind or remember is the velocity potential from the wave surface, okay? We differentiate with respect to time, multiply by rho, and replace it into here, and that's the Froh-Dekry law, right? In this case, we're taking the dot product, okay? And that's why we get N3, little N3 here. And then what we do is we apply strip theory, okay? So for each one of these strips, okay, we consider a 2D problem, okay? And that's why we express this expression with a large N3 here. That implies immediately that N1 is small and neglectable. So basically, for each one of these strips, okay, we have to solve a 2D problem. That's what the strip theory says. So that's this one. Now here, we have a big problem because N, okay, changes in the section, right? So this depends on this position along the section. And also, e to the kz also changes, okay? Because if you move along the section, the z will change, right? And the problem is that this variation, okay, does not follow any specific mathematical function. So we're going to do a trick in order to solve this in a decent way. Okay. So this trick is that we take a representative value for z in the section. And since it's a value for the whole section, doesn't change with the position on the section. So we can take this outside this integral. So we're left only with this. Now, to evaluate T star, there are many ways to do it. Okay, this is the classical one. Okay, so you calculate the area of the section divided by the beam of the section, and that's your T star. Now, we have to be careful because here we locate the origin of the reference system. So the Z, which goes with this T star, is negative, right? So we cannot forget this negative sign here. But in general, this T star changes with the position, with the section. Now, after we do this integral, it's could be simplified, okay? This N3 is the cosine, okay? Cosine in the vertical direction of the normal. And dl N3, okay, is the negative of dy, okay? So if we have this negative, then we can integrate this and get the integration of dy. So you integrate dy from one side to the other, okay? I'm sorry, here. From one side to the other, dy, because this is the y direction, from here to here. And basically you obtain B, the beam in the section. So this is the result for the Froh-Dekry law force component. And this is a very good approximation in cases, for example, when we receive the waves from the bow, okay? Because in that case, the wavelength, you have to compare it basically with the beam. And in general, okay, the wavelength is much larger than the beam of the ship. So this is a very good approximation for that. Okay, now let's go to the other component. In this case, we make an observation, okay? To calculate the hydrodynamic forces, okay, we do is this. We move the ship up and down, and we see that there are some waves which are being generated. And that's this problem. We calculate phi3, and we see that there are some waves which are moving away from the ship. This is the case that we're solving right now. We have the ship, no motion. Remember, this is partial. So the only different than zero parameter that we consider are the waves, the incoming waves. And once the wave reach the hull, they diffract. So it's like they move away. So it's similar to this one here. Okay, so the shape is similar, and you see there are some waves which are moving away from the ship, which is something that happens here. So people thought that this problem, which was already solved, can be used to solve this one here, which is the one that we're trying to calculate. Okay, so this is the way we should do it. Okay, this is Gauss theorem that we reviewed in chapter 2. So we apply in this Gauss theorem the same theorem, but using these two functions. These are vector functions. Okay. Once you do this, you plug it into here side. So what we can do is we can take the difference between these two, this cancel, the difference is equal to 0. Okay. Now, remember, phi3, this one here, is the velocity potential per unit velocity. Okay. So this we know. This phi sub d is the one that we're trying to obtain. Okay. So this term we know. And in the next step, this is going to be replaced by the incident waves. So we can represent this, which we do not know, by this one here, which we have already calculated. Not directly, but these two pieces are already calculated. Here, we see the hull is not moving. So on the hull surface, the derivative of the potential function, which is the combination of the incident and the diffraction in the normal direction, has to be equal to 0 in order to avoid any velocity in the normal direction. Okay. So d phi dn, d phi d dn has to be equal to minus d phi I dn. And this is what. But d phi I is the incident wave, so we know that. So we know that. Now this one here is the velocity potential per unit velocity, and we deduced that this is equal to the component of the normal in the vertical direction, n3. But this, you can recognize that this is proportional to the force, okay? So we're going to replace this in terms of this. And this is the velocity potential that we already know because this was solved for the aerial mass and damping coefficient. And this is the incident waves that, of course, we know. So S3, considering both components, okay, the incident waves and phi sub d, this, remember, basically it's the Frode-Krylov component, and this is the one that we're trying to determine. So we have phi d, and part is going to be replaced by this thing. What do we know already? Okay, so this is the transformation that we do. So the first term is the Frode-Krylov component, and the second term is the diffraction, but now the diffraction has been expressed in terms of phi3 that we know, and the incidence wave that we also know. So we can apply these two parameters that we know, combine it in this way, integrated, and that will give us the diffraction component of the vertical excitation force. Okay, now the phi dn in the preview in this here that we're trying to determine. Okay, now we know that there is no y component in the incident waves because we consider that as a 2D problem. The normal can be simplified using the SubChp assumption. So N1 is small and neglectable. So if we take this dot product, the only term which is going to survive is the third component. So this dot give you this. Okay, the other terms are basically equal to 0. So this term here is going to be replaced by this one here. That's what we have. So instead of d phi dn, we put d phi dz and 3. So we can integrate this part, okay, for each section, and then we integrate along the length of the ship to calculate the diffraction component. Okay. So this is the phi. We recognize that. Z0 is the amplitude of the wave system, omega frequency, e to the kz. K is the wave number. So we replace this into here. So we have a K somewhere in here. Here is a K, and that's what we have. Okay, I forgot by mistake. I did not include this expression. So I'm going to pick up from this point. And so I prepared a new slide here. You have these expressions in your class notes, okay? So this is the equation in the previous slide, and we're going to review this in detail. Now, we have to recognize what terms are function of x and what terms depend on the position on the section, okay? So, of course, this is the normal that depends on the position of the section. This phi3 depends on the section, so we have to integrate this. But this expression we show in chapter, in this chapter, at the beginning of this chapter, that it is equal to this combination. And that's something that we were expecting, right? Because phi3, okay, is related to the calculation of added mass and damping coefficient. So the integration of this is what we obtain. It makes sense, we have said several times, right? Because what we do on the surface, when we move up and down in the surface, generates waves. And that waves depend on the frequency. And the result of the integration gives you added mass and damping coefficient. So that's the solution. After we do this, we can simply integrate along the length of the ship, combine it with these other terms. And what we do is, since there is no analytical solution for this, is simply apply a numerical integration. That's all. We can use Newton's one of the first law, Simpson law. So here we have the whole thing. Okay, so this term here is the Frode-Curie law, and this other term here, which is this one here, is the diffraction coefficient. In general, when we calculate this in the vertical plane, or no, not in the vertical plane, when consider waves coming from the bow, okay? Usually this term here is the most important. But I want you to calculate that, and you can conclude about this simplification, okay? So in that, then you can say by experience, okay, this is the most important component when you receive waves from the bow, only in that case, okay? So we have to be careful because this term here is the imaginary term. So we have two terms which are real and one imaginary. And then you have to integrate, okay? So here also you have complex. So what you do is you simply keep track of real and imaginary and then proceed to integrate, okay? Now, finally, this in detail, okay, corresponds to the force, but we also have to consider the rotation, okay? So if this is X, this is X, this is Z, then entering in the plane is the direction Y. So this is the positive eta phi, okay? So if we have a positive force, this is wrong. This should read DFD, okay? Because this is a force. This force, okay, multiplied by this arm will produce, you can see it will produce a negative moment because this is a positive. We'll try to go in this direction, which is negative. So we can get the same expression except for this and for this as the acting moment that we need to calculate from the waves. Okay. Any questions so far, people? Any questions that we have what we have done? This is just a review of the previous session. I don't know if you have any questions.
I have a question, Dr. Arnold Manrique. Good afternoon.
Hello.
How I know to the result of the wave in the bow, the pressure G and Bx is correct. How is
the pressure on the bow? Well, the thing is this, right? You have two components. One component is the component from the Krylov.
Yeah, this component. Is my question. How do I know that the Krylov is correct? Or maybe to the good.
In general,
yeah.
In general, what we can do is this, okay? I see if I can draw. See, if you have the ship, you receive waves in this direction, okay? What you can do is, you know lambda, or you can get, for example, a lambda close to the length of the ship. What you can do is you can calculate this force for several instances of time, okay? And what you can try to check is that if the relationship between the force and the relative position between the wave and the ship makes any sense or not. For example, if I have something like this, okay, let me change color. Something like this. Would you expect a high value of force or a low value of the force? Again, would you expect a high value of the force or a low value of the force? Mr. Manrique, please.
Yeah.
A high value or a low value of the force?
I think the high value of the force.
Yes, yes, because usually around the midship section, you have the larger beam, the higher uh, transfer area, right? So since I'm drawing here a crest, that means that there is a lot of force pointing upward. Okay? Let me change color again. Similarly, if we have a situation like the opposite one, right? For example, something like this. So we have like this. You have a low draft in here. So probably you will have a component which points downward. So you will have probably a negative value of that. So that's what you should try to do, okay? You should try to check, okay, to draw at different positions the wave profile, and see if that makes sense or not.
Similar to the hugging and sagging.
Yeah, you want, okay.
Similar to
yeah,
the
similar, but that's the idea, right? When you have the crest, when you have the crest around midship, you can expect a lot of extra buoyancy pointing upward. And you have when you have the throw around the midship section, yeah, you have a deficiency in buoyancy force. That means that the net force will be pointing downwards. So yeah, more or less that's the idea. Does that make sense or not? 7 years ago, we have a program. Well, not we, I mean, I just took it from the literature. It's called SCORES. We used to use it widely, and we got a lot of numbers, lots of numbers. So I wanted to see if that makes sense or not. So what I did was I prepared a program so we can see the response of the ship according to the waves, incoming waves. And what I did was I asked an officer from the Navy. He was a student at that time. So I called him to my office, and on the screen, okay, we see that the relative situation, okay? And I asked him, does that make sense to you? Is that physical? And he said, yeah, it makes sense. So in that case, yes, when the wave came on the bow, after a little bit of time, finally the ship started to respond, and they start having something like that. So the relationship between, or the phase lag between the incoming waves and the response of the ship made some physical sense. Similarly, in this case, you can do this. Okay. Any other question, people? Any other question that we can try to answer? We can do this. I can explain how to do this using Excel, right? Because in Excel, you can input, for example, a value for the vertical displacement and for the rotation. And you can take points, okay, describing the profile of the ship. And knowing the vertical displacement and the rotation, you can plot the new position, okay, of the ship. Also, if I give you a time, you can plot the position, different position of the wave profile. So that's that's a way to check if our results make some sense or not. Okay, if there are no questions, then I'm going to go on with it.
Good afternoon. Sorry. Question.
Yeah.
It's about you have determined this is force F3 and 5. You have the solution in the section transversal is constant or variable.
Okay. All of this inside the integrand, okay, everything here, I can write, all of these All of this is function of X in general. For example, the T star, you have to calculate the T star in a section, okay? So if, for example, in a ship, okay, in a ship, for example, in the bow, you have something like this. In the midship area, you have something like this. Around the propeller, you have something like this. So T star will change according to the position along the length of the ship. Definitely, the beam changes with the position. Okay. Added mass, the damping coefficient, yeah, according to the section, changes the A33 and B33. So basically, everything inside here changes with the position along the length of the ship. There is nothing constant in general. There are some examples, extreme examples that we have to use, for example, for the homework and things like that. But those are extreme simplifications. For example, if you consider a box barge, yeah, in that case, the beam is constant. In that case, the draft is constant, things like that. But in general, every parameter in this integrand depends on time. Any other question, people? Any other question? And I'm going to go on. Okay, this is something that very interesting, because this is the shape of a ship. I don't know, maybe you have seen it. We have something similar to this in our lab, okay? It's a gray model, right? The sides are vertical and the plane is parabolic, right? So it starts at 0, increases, and then reduces slowly to 0 back in the aft. So it's this one basically, and you know that this is not the ship, right? Because in the ship usually there is some flare on the forward, and the aft you have to leave space for the propeller. But in general, this is a good example, as you can see, and you will see. Okay, so this is the floater-Kirillov component. And for this case, we need to include the variation of the beam along the length of the ship. In this case, this T star is constant, since every section is rectangular and there is no trim, okay? But as I said before, this is just a simplification, okay? So we can develop this integration completely. So we can take this outside. So we will have e to the ikx, and this bx has one constant and one term which is quadratic. So there is an integral exact for this integration. I did it, so you can do it too, okay? And so we replace, instead of this, we replace this, and you can do the integration, evaluating both ends, and this is the result, okay? And you can immediately think, wait a minute, this is not a ship. So this expression must be way off. And let me tell you that these are the results, okay? The results show that example, this is the parabolic water plane. This is the other is the result for a I'm sorry, this is not. This is just he's comparing the influence of the diffraction force, okay? In this case, the waves are coming from the bow. And you see that the difference is very small. So from this graph, we can say that the influence of the diffraction in this situation, waves coming from the bow, are neglectable. Okay. Now, the other curve is very nice. I mean, here I have, this is the force, exciting force in heave, and you see the shape. You see the shape here, and this is for the Series 60. So this is a series of ships which were developed, I think it was in the 1960s, last century. Okay, it was very popular in the past. And you see here that Professor Trosh included these values, these evaluations, okay, for evaluation. Okay, these points here are evaluations of this formula. The others are results, experimental results. I was trying to find these results to give you as an exercise, but I couldn't find them because I cannot read these values. I'll keep trying. Hopefully by Thursday, I will be able to show it to you. Okay, but the thing is here is that this, remember, this is for the parabolic water plane hull, and this is for the Series 60. And it's still this expression that comes from a very simplified form follows relatively close the real results. So even though this comes from a very simplified situation, can help us to understand many things in this problem. Okay? One very, very important aspect is that for very low frequencies, okay, very high wavelength or very low frequencies, okay, this ratio reaches 1. Okay, this is rho g, that's a specific weight. This is the area of the water plane, and this is z of 0. This is the amplitude of the wave. And that means that the force with very basically equal to this thing here. Okay, and if you apply this, since you are in the very low frequency range, very low, you can neglect all dynamics. So basically you have a force which does not depend on time, no acceleration, no velocity. So the only term that we have is kz3. Okay? And in this case, you remember that K is equal to A of the water plane times gamma. So you put this in the denominator, okay? And you simplify rho GA, and basically you get the amplitude of the wave. So for very, 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 very long waves, the ship doesn't move relatively to the wave. Basically, for very long waves, okay, what the ship does is it goes up and down with the wave. So the maximum value that it takes corresponds to the wave amplitude. Similarly, in the other direction, plus amplitude of the wave minus amplitude of the wave. There is nothing in dynamics. It's very slow. It's a very, I mean, this is something that we can always check, especially when we go in a small boat and we face very long waves. And you see basically that the boat goes up and down with the waves. So that's that. No questions? See, what we have done so far is just review from the previous session, okay? That's all. Okay, it's 4:50. Let's take a 5-minute break. And when we continue, when we come back, we are going to check the solution, okay? So we're